Let me tell you about one of the most elegant ideas in all of mathematics. It starts with a simple symbol, n factorial. That exclamation mark is not just for emphasis. It represents a concept so fundamental, so deeply woven into mathematics, that it shows up everywhere. From the games we play to the equations that describe our universe. Let's start with a question that seems almost too simple. Imagine you have 3 books sitting on a shelf. In how many different ways can you arrange them? 3 books, different orders, how many possibilities? Let's work through this step by step. For the first position, you have 3 choices. Any of the 3 books could go there. Once you've placed the first book, you have 2 choices left for the second position. And for the last spot, only 1 book left. So the total is 3 times 2 times 1, which equals 6. This pattern of multiplying descending numbers is exactly what factorial captures. Let's see all 6 arrangements. ABC is the first one, ACB is the second, then BCA, and finally CBA. 6 arrangements total. We write this as 3 factorial equals 6, a simple counting problem, and the answer is a product of descending numbers. That's the beauty of factorial. Now let's write this down formally. N factorial is defined as n multiplied by n minus 1 multiplied by n minus 2, and you keep going all the way down until you reach 1. Let's see some examples. 4 factorial is 4 times 3 times 2 times 1, which gives us 24. 5 factorial is 120. And 6 factorial, 720. Now, here's something that might seem strange at first. What about 0 factorial? By convention, 0 factorial is defined to be 1. It might seem odd, but this definition makes many mathematical formulas work out beautifully. It's not arbitrary, it's deeply connected to how factorials appear in other equations. Now here's where factorial gets really interesting. Let's watch how fast it grows. 1 factorial is just 1. 2 factorial is 2. 3 factorial, 6. 4 factorial, 24. 5 factorial jumps to 120. 6 factorial, 720. And 7 factorial, over 5,000. But let's keep going. By the time you reach 10 factorial, you're already at 3.6 million. 15 factorial, over 1 trillion. And 20 factorial is more than 2 quintillion. That's a 2 with 18 zeros after it. Factorial doesn't just grow fast. It grows faster than any exponential function you can think of. It's explosively fast. So where does all this rapid growth actually matter in the real world? Let's start with probability, the mathematics of chance. Factorials are absolutely essential here. They're the building blocks for calculating odds, for understanding how likely or unlikely events really are. First, let's talk about permutations. This is when you're selecting some items from a larger group, and the order you select them matters. The formula uses factorials. P of n comma r equals n factorial divided by n minus r factorial. Here's a real example. Say you're running a race with 4 people, A, B, C, and D. You want to know how many different ways you can award first and second place. We plug into our formula. P of 4 comma 2 equals 4 factorial divided by 2 factorial. That's 24 divided by 2, which gives us 12. 12 different ways to award first and second place. The order matters here. A in first and B in second is different from B in first and A in second. Now let's look at combinations. This is different. With combinations, you only care about which items you choose, not the order you choose them in. The formula looks similar, but now we divide by r factorial as well. This removes all the duplicate orderings. Think about a lottery. You pick 6 numbers from a pool of 49. When the numbers are drawn, does it matter what order they come out? No, you just need to match the 6 numbers, regardless of sequence. When you calculate C of 49, 6, the answer is almost 14 million. That's your odds of winning, 1 in 14 million. Factorials tell us exactly, precisely, how unlikely hitting that jackpot really is. Our second application takes us somewhere different, into the world of computer science. Here, Factorial growth creates some of the hardest problems we know. Problems that even our most powerful computers struggle with. Consider one of the most famous problems in computer science, the traveling salesman problem. Imagine you're a salesman. You have a list of cities you need to visit. You start from your home city, marked S here. Your goal is simple. Find the shortest route that visits every city exactly once and returns home. Sounds straightforward, right? Just try all possible routes and pick the shortest one. But here's the problem. For n cities, the number of possible routes is n-1 factorial divided by 2. With just 10 cities, there are over 180,000 routes to check. That's manageable. But 15 cities, 43 billion routes. 20 cities, 60 quadrillion. Even if your computer checks 1 million routes per second, it would take over 1,000 years. This is why computer scientists call these problems computationally intractable. The factorial growth of possibilities defeats even our fastest machines. Our third application might be the most surprising. Factorials appear throughout physics and engineering, hidden inside one of calculus's most powerful tools. The Taylor series is one of the most beautiful ideas in mathematics. It lets us approximate complicated functions using simple polynomials. Take the function e to the x, this red curve. It appears everywhere in science, from radioactive decay to population growth to compound interest. And here's how we can write it as a Taylor series. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, forever. Notice where the factorials appear. In every denominator, 2 factorial, 3 factorial, 4 factorial. And these factorials are absolutely crucial. Watch what happens as we add more terms to our approximation. With just 2 terms, we get a rough approximation. Add more terms, and it gets closer. More terms even closer. Keep going, and eventually it matches perfectly. The key insight is that those growing factorials in the denominators make each term shrink rapidly. The denominators grow so fast that the series converges. Factorials tame infinity. Now, I want to show you something truly remarkable. What is 1/2 factorial? Now wait, that seems like a strange question. We defined factorial as multiplying whole numbers. How can you have half of something in the multiplication chain? But mathematicians, they found a way. It's called the gamma function. The gamma function is a beautiful extension of factorial. For positive integers, gamma of n equals n-1 factorial. But here's the magic. The gamma function works for all numbers, not just whole numbers, fractions, decimals, even complex numbers with imaginary parts. So what is 1/2 factorial? The answer is the square root of pi divided by 2. Think about that for a moment. Pi, the number we associate with circles appearing in factorial, a concept we define by counting arrangements of books on a shelf. This is the kind of unexpected connection that makes mathematics so beautiful. It tells us that factorial is just one piece of a much deeper, much more profound mathematical structure. So let's step back and see what we've discovered. Factorial started with the simplest possible question. How many ways can you arrange 3 books on a shelf? It reaches into probability, computer science, physics, and pure mathematics. From counting books on a shelf to the edges of mathematical infinity. That's the factorial. A simple idea with profound reach. Thank you for joining me on this mathematical journey. Subscribe for more math visualizations.